Now I want to discuss another theorem that shows up in section 1.7 of your book, although we did not discuss this much last semester. So let's let X be a closed subset of the real numbers. And let's let F be a function who's from X to R. And then we're going to suppose that F is bounded and continuous. And the conclusion is that there exists a function h whose domain is all of the real numbers, whose range is the real numbers, such that h is also bounded and continuous. And h of x is equal to f of x for all x in our original domain. I'm not going to write out the proof of this thing in detail, but just to give you some ideas, here's our real line. Then here is our closed subset F. And then we've got our function F. It's doing whatever it is going to do. It's continuous on all these little pieces of our closed set. And then the idea is, in the real numbers at least, the complement of a closed set is the union of open intervals. So on each open interval, you just grab the values at the endpoints and you do a straight line interpolation. Unless there is an half-infinite interval at the end, in which case you do just a straight horizontal interpolation. And that gives you something that's, not only bounded, it's got the same bounds as the function you started with. Now, this theorem is not like the theorems we saw earlier in section 5.4.1. You don't need anything else if your domain, if you've got a function defined on a closed subset of an arbitrary metric space and mapping into the reals, you can extend it to the rest of the metric space. So we don't need to wait for compactness or connectedness. It's not like the extreme or intermediate value theorems, which really aren't true. For arbitrary metric spaces, you need extra structure. On the other hand, this theorem is not like the other theorems we talked about earlier, where the proof of it in a general metric space is exactly like the proof of it in the real numbers. You need a completely different proof. And you're actually going to provide the completely different proof on your homework. That's going to be your homework assignment for this video. But in this video, I'm going to prove Urysohn's lemma, which is the major tool you need for proving the generalization. So let's start off by reminding ourselves what a Lipschitz function is. Your book thinks this is an example, but it's really a definition and a proposition. So let's say we've got two metric spaces. And we've got a function between them. And then if there is a constant m, that is a positive real number such that if you take 2 points in our domain, then the distance between their images is never any more than m times the distance between the inputs, then we say that f is Lipschitz. And here is a proposition about Lipschitz functions. This is the generalization of proposition 1.7.14, which your book just packs into example 5.4.12a. And that's that if f is Lipschitz, then f is uniformly continuous and therefore regular continuous. And the proof of this is pretty straightforward. So why don't I go ahead and write it down, pick a positive number epsilon, and we're going to let delta be just epsilon over m. And then if you've got 2 points whose distance is less than delta, then by definition of Lipschitz, the distance between their images that's less than m times the distance, less than or equal to, in this case, the distance between the 2 points, which is less than m times delta, which is just epsilon. And so that's precisely the definition of uniform continuity, which obviously implies regular continuity. Now let me give you a particular function that is Lipschitz, and we're going to use, well, certainly we're going to use that it is Lipschitz and uniformly continuous and all that good stuff. Let's let XD be a metric space. And we're going to let A be a non-empty subset of our metric space. Then the function f, whose domain is x and whose range is the real numbers given by f of x is the distance from x to a. Let me remind you what the distance is. It's the infimum of the distance from x to little a, where all the little a's in our set A. And since I said A was a non-empty set, this infimum is going to be a non-negative real number. This is a Lipschitz function. With Lipschitz constant. At most 1. And by that, I mean that the number m in the definition of Lipschitz constant, m equals 1 will definitely work. Possibly some smaller m's will work, but m equals 1, I'll promise you, works.
Let's prove this.
So let's let x and y be 2 points in our metric space, and let's pick some point A in our set. Now, what we're trying to prove is that f of x minus f of y is less than the distance from x to y. Yep. That's what it means to be Lipschitz. But since the f of x, that's the distance from x to a, is defined in terms of these a's, we'll end up taking an infimum over the little a's. So now, by the triangle inequality, or rather the reverse triangle inequality, but it doesn't really matter. The distance from our point x to our arbitrary point in the set, that's at least the distance from a to y, and then we subtract minus the distance from y to x. We proved the reverse triangle inequality back in section 5.1, but I don't feel like looking up the proposition number. If it bothers you, just move the distance from y to x over to the other side and use the symmetry of the metric, and you'll see it's equivalent to the regular triangle inequality. But then the distance from a to y, that's the distance from y to a, that's at least the infimum of all the distances from y to, I suppose I'd better use a different letter, y to alpha, such that alpha is in a. Oh, we've still got to subtract off the distance from y to x. So, and notice that that infimum has a name. It's the distance. When I say it, I always say distance, but for distance from a point to a set, and also distance from a point to a point, but the functions are named dist or d. So the conclusion is that this quantity, distance from y to a, minus dyx, is it's less than the distance from x to a, where a was any element of a. So this is a lower bound on this set, the set of all distances from x to a, such that a is in a. So distance from y to a minus dyx. If it's a lower bound, it can't be any bigger than the greatest lower bound. And that's better known as the distance from x to a. And then we just rearrange this inequality. Remember, you can always add things to both sides of an inequality and it will still be true. We have that the distance from y to a minus the distance from x to a, that's less than or equal to the distance from y to x. And similarly, the distance from x to a minus the distance from y to a, is less than or equal to the distance from x to y. So taking the absolute values, if you who can bound something in its negation, so F is Lipschitz. With m equals 1. It's possible that there's some lower value of m that works, but we know m equals 1 definitely works. So now is a actually quite powerful and quite useful theorem. It's important enough to be named after a particular person. So let's let XD be a metric space. And we're going to let F and D, they're both subsets of X. They are disjoint. And F and D are both closed. Then there is a function F, it's a function from X to the real numbers that is continuous. And satisfies f of x is 1 if x is in f, f of x is 0 if x is in D, and f of x is between 0 and 1 if x is anywhere else. The proof is, well, we're going to write it down pretty quickly, but it builds on a lot of work we've already done. So by proposition 5.3.9a, f is equal to the closure of f, because by assumption f is closed. And then by proposition 5.3.17, closure of f is the distance, is the set of all points in X whose distance to f is 0. So f is the set of all points where whose distance from f is 0, and the same thing is true for D. This is where we are using that the two sets are closed. And since F intersect D is the empty set, and The distance from x to f is non-negative. The distance from x to d is also non-negative. We have that. If you take the two distances and sum them, you're always going to get a positive number. Because f and d are disjoint, there are no points in both f and d, so there are no points where both of the distances are equal to 0. Every point either the distance to f is positive or the distance to d is positive, or maybe both. And since your distance is never negative, when you add the two distances together, one of them is always positive, the other one can't be negative, so you cannot get 0. Thus, the function g, if g of x is this thing we've written down, distance from x to f plus the distance from x to d, then g is defined for all points in x, and it has a range, the positive real numbers. And by the previous proposition, the two components, distance to f, distance to d, those are both continuous functions. So by proposition, but if 0.4, 0.5a, and the theorem we just proved, proposition 5.4.7, g is continuous. Let's let h of x be 1 over x, and then by a corollary 1.7.3b. I don't mean the generalization of 1.7.3b to metric spaces. I mean, honestly, corollary 1.7.3b, because h is a function from real numbers. H is continuous from the positive real numbers to the positive real numbers is continuous. So we have that. Let's write it. K of x is 1 over the distance to f plus the distance to d. That is continuous from x to the non-negative real numbers. And that is by proposition 5.4.4. Because h is the composition of the continuous function h with the continuous function g, k must itself be continuous. So now we're going to let f of x, that we're going to take our k function, or we're going to multiply it by the distance from x to d. And what we get, of course, is the distance from x to d, and that is divided by the distance from x to d plus the distance from x to f. And then f is a continuous function times our function k, so that is by proposition 5.4.5c, which is all about functions mapping into the RP and as a special case into the real numbers. F is continuous. Function from our metric space x into the real numbers. Then if x is in D, then the distance from x to D, that's no more than the distance from x to itself is 0. So f of x equals 0. If x is in F, then the distance from x to f is 0. The distance from x to D, well, it doesn't matter really what it is, but we saw before it was positive. So f of x is a positive number. This distance divided by itself, which must be 1. And finally, let's look at what happens if x is in x but is not in either f or d. Then the distance from x to d is positive, but so is the distance from x to f. So if we add the distance from x to f, we're going to get bigger. So we've got that 0 is less than f of x is less than 1. And that completes the proof. One thing I want to point out to you is that Urysohn's function might not be Lipschitz. So here is an example. Let's let x be R2, and we'll let d be, let's take the Euclidean metric. Where x1 and x2 are the two coordinates of x, y1 and y2 are the two coordinates of x, of y. We're going to let d be the diagonal. We'll take that as all the points x1, such that x1 is a real number. And we'll let f be this hyperbola. We'll take it as the set of all points x1, x2, such that x1 squared is x2 squared plus 1. And for those of you who remember your high school algebra well enough, we can go ahead and draw this hyperbola. Here is our diagonal d, and here is our hyperbola, which is eventually going to approach our diagonal. So, and it sort of doesn't matter, and the particular function I've given you, you can see he is going to be very non-Lipschitz, is going to change very steeply in regions like this one here along the diagonal where f and d are very close to each other. And you can't fix this by picking a better function. You've got to get from 0 here to 1 here, and you've got to do it very, very quickly. So Urysohn's function is not necessarily going to give you a Lipschitz function or even a uniformly continuous function. However, that's only happening because our D and F, they are getting closer and closer together. So if we've got two regions, D and F, that are in fact a positive distance from each other, we can avoid this. So let's make this precise. Let's let delta be the distance from D to F. This is defined exactly as you'd think. So let's call it the distance. Let's call our points X and Y. Since X is in D, Y is in F. Since I really don't want to call my points little d and little f. And suppose that delta is positive. Then there is a function f that is Lipschitz with m, in fact, equal to 1 over delta that satisfies these conditions. So when we prove this, we're going to end up using a different function f than we saw before, just because it makes it a lot easier to prove it's Lipschitz with the bound we want. So here is our region D. Here is our region F, and then delta is this distance between them. Now, first I'm going to prove that m has to be at least delta. So let's suppose f of x equals 1 if x is in our set F, f of x equals 0 if x is in our set D. And let's pick positive number epsilon and let x and y, x is in F, y is in D, and the distance from x to y is less than delta plus, let's make it epsilon over delta. Actually, let's just make this epsilon. Then if f is Lipschitz, then we can write out this long chain. 1 is absolute value of f of x minus f of y by definition of f, and then because it's Lipschitz, that's at most m times the distance from x to y, which is less than m times delta plus epsilon. And since delta and epsilon are positive, so m has to be greater than 1 over delta plus epsilon. This is true for all epsilon greater than 0. So we've got that m has to be at least 1 over delta. Now let's go ahead and define our f. We're going to let f of x be, this is going to be a little annoying, but you take the distance from x to d, and then you're going to divide that by 2 times delta. That's 2 times the distance from d to f. And then you're going to either take that or you're going to take 1/2, whichever of those two is smaller. And then you're going to add to that, you're going to add either 0 or 1/2 minus the distance from x to f over 2 delta, and then you subtract that from 1/2. Here's a picture of our f in the real numbers. There's our coordinate axes. Here is our region D, our region F. And then what we do is we start with this function. It's 0 in D. It builds up slowly until you get to 1/2, and then it's 1/2 after that. And then you start with then you have this function. It's 1/2 in F. It builds down as you move away from F, and it is 0 after that. And then when you add them together, you get something that's 0 in D, that's 1 in F, and sort of ratchets down and up outside of that. So let's check and make sure this has our properties. If x is in D, then the distance from x to D is 0. And the distance from x to f, well, the distance from x to any particular point in f is at least delta, so the distance from x to f also has to be at least delta. So f of x, that's the minimum of distance from x to d to 0 is 0, so our minimum is going to end up being 0, and then the maximum is going to be 0, and then 1/2 minus distance from x to f over 2 delta. But this quantity here, that's at least 1/2. So the whole thing simplifies down to 0. And similarly, if x is in f, then the distance from x to d is at least delta. The distance from x to f is 0. So f of x is the minimum of distance from x to d over 2 delta. That's at least 1/2. So our minimum in this case, it's going to be 1/2, and then we add to it the maximum of 0 and 1/2 minus 0. Both of these guys come out to 1/2, so that's 1/2 plus 1/2 is 1. We're going to notice that if x is in x, then f of x, it's the sum of 2 things, and both of them are between 0 and half. But the first part is, the minimum of something non-negative with 1/2, so that's between 0 and 1/2. The second thing is the maximum of 0 and something that's at most 1/2, so that's going to be at least 0 and at most 1/2. Then it's pretty clear that if you think about it for a moment, the distance from x to d over 2 delta, the first thing you're adding up is at least the distance from x to d over 2 delta. So that gives you a lower bound on f of x. And then an upper bound, the first thing can't be any more than 1/2. The second thing can't be any more than a half minus the distance from x to f over 2 delta. That's 1 minus your distance. So if x is in x but is not in f or d, then your left-hand side is positive. Your right-hand side is less than 1, so f of x is between 0 and 1. Now let's show that this thing really is Lipschitz with the m I gave you. Let's let this will be easier if we define some helper functions. We'll let g of x be our distance from x to d over 2 delta, and k of x, we'll take that to be the minimum of 1/2 and g of x. And then if x and y are in x, then k of x, which is, remember, a piece of our f of x, we take k of x minus k of y. Let's take some absolute values, and we're going to have, as it happens, 4 cases. So first option is that g of x and g of y are both 1/2. In which case k of x, k of x and k of y are both 1/2, meaning g of x is at least 1/2, g of y is at least 1/2, in which case k of x minus k of y is 0. Second option is that k of x is less than 1/2, k of y is also less than 1/2, in which case the k's are both g's, so we're left with g of x minus g of y, absolute value. Third option is that k of x is 1/2 and g of y or k of y, whichever you want, is less than 1/2. So then we're left with 1/2 minus g of y, and we know that g of y is k of y is less than 1/2. So this is less than g of x, less than or equal to g of x minus g of y. Third option is the reverse. And in this case, we're going to have g of y being k of y being 1/2, k of x being g of x. So in any case, k of x minus k of y is less than or equal to g of x minus g of y. And because g of x is the distance function, which is Lipschitz, and then the 1 over 2 delta, 1 over 2 delta distance from x to y. And then I don't feel like writing out the argument again, and it's pretty similar. If the other piece, h of x, is the maximum of 0, 1/2 minus 1 over 2 delta distance from x to f, then h of x minus h of y less than or equal to 1 over 2 delta distance from x to y. So since f of x is k of x plus h of x, we have that f of x minus f of y less than or equal to 1 over delta distance from x to y. And that shows that our function is Lipschitz with the constant we expected, and that completes the proof.